Okay, so today we're talking still floating point numbers, and this is basically how in R we have type double, right? Type double. This means the number is represented with 64 bits, okay? So somewhere in the computer there is basically 64 little like transistors that are either in the 0 or 1 position. And this is how we represent a number, okay? You might ask, what about single, right? How is it already type double? Well, there is such a thing as type single, but it doesn't exist in R, okay? So in C and in Python and in other languages, you have 32-bit floating point numbers, okay? It uses half as much memory, and you do calculations that way. Okay, but anyway, with these 64 bits, we break them up into you'll have one sign bit, okay, and then 11 bits for the exponent, okay, and the remaining 52 bits are for the mantissa. Okay. And then just for illustration, we will use a mini float, which has 8 bits, one sign bit, 3 bits for the exponent, and 4 bits for the mantissa. And we said that the exponent uses a biased scheme. Okay, and so for 3 bits, the bias is equal to 2 to the 3 minus 1 minus 1. Okay, which is going to be bias is 3. So that if you have 0, 0, 0 in the exponent, this corresponds to 2 to the negative 3, and if you have something like 1, 1, 0, which is normally 6, becomes 2 to the 3, because you do 6 minus 3 to get your bias. Okay, what would be the bias for a double float? So we have 11 bits in the exponent. So the bias would equal 2 to the 11 minus 1 minus 1. So 2 to the 10 is 1024 minus 1. So we have 1023. This is our bias. So if you have 0, 0, 0, 11 zeros in the exponent, this would correspond to 2 to the negative 1023. Okay. Yeah, that's actually there's a technicality here. So, but basically, you just take whatever, you translate it. You know what? Let me let me modify things so these are technically correct, because these are currently, as I have it written, it is not technically correct, so which I guess is just not correct. So let me just say 0, 0, 1 in the exponent would correspond to 2 to the negative 2. You do 1 minus 3 is negative 2, and 0, 0, 0, 0, 1 would be negative 10 to the 22. Okay. Okay, so you just take whatever your exponent is in binary, and then you subtract off the bias. Okay. So I think we did like a little practice problem, right? So let's say I have this. And so let's say I have 1 and 0, 1, 1, and 0, 1, 1, 0. Okay? What is this in decimal? So this is mini float. Okay? What is this in decimal? Okay. All right, let's go ahead and break this down. This is our sign. The sign is going to be negative. Okay. Our exponent is 1, 1. This is in binary. What is that? 3. So with the bias, it's equal to 0. So we basically have 2 to the 0 right here. And then this is our mantissa. And so this is going to be, this corresponds because we're going to always assume there's a 1. So it's going to be 1 point, and then we take in our 4 bits. So we have 0, 1, 1, 0. Okay, so I have 1.1 plus 0 halves plus 1/4 plus 1/8. Okay, and so here this gives me 1 3/8, or 1.375 times 2 to the 0. So this, and I have a sign of -1, so this becomes negative 1.375. Question, yes?
On the last slide, when you changed the 1023 to 1022, why did you do that again?
Because technically when it's all zeros, it's not negative 1023. I'll explain, all right? But
Okay.
we'll get into this, what we call denormalized numbers. So it is correct on the last slide, if it's all zeros and a 1, then that corresponds to binary to 1, and then you throw in the bias and you would be at 1 minus 1023 at negative 1022. Okay, that is correct, right? When you put in all zeros in the exponent, things change, and we'll talk about that in like 2 slides. Okay? All right, is this okay? Going from, I don't know, this mini float to decimal representation, right? All right, let's take a look at. Oh, okay. Well, and then what's the next number that I would represent? So the next number in the sequence would be 1, 0, 1, 1, 0, 1, 1, 1. Right? This would be the next possible, I guess, number that's larger in magnitude. Okay. And so this corresponds to a mantissa of 1.0111, and that would be 1 plus 1/4 plus 1/8 plus 1/16 what is that? Oh, 1/16 is 0.0625, so what is it? Okay, so it would have 1.4275, is that right? Okay, so that would be the next biggest number that I can represent. Okay, so it is not possible to represent in our mini float scheme, it's not possible to represent the number 1.4. Okay, if we tried to enter 1.4, it will either be 1.4275 or 1.375, and between those two numbers, 1.4275 is closer, and so 1.4 would become 1.4275. Okay, if you wanted to try to do 1.38, it's not possible. You'd have to settle with 1.375. Yes? Oh yeah, this is also negative, sorry. Okay, so yeah. So if you want something like negative 1.38, it's going to just pick the next closest thing, negative 1.375. If you want negative 1.40, it's got to figure out, and then it'll say, okay, this is the one, all right? And so at this point, basically, your increments, the values are spaced out at by 1/16. Okay, so that's the highest level of kind of precision you can have between two numbers at this point in our number line. Okay, it changes. This is kind of the neat thing about floating point, is that as you get bigger numbers, the numbers get more and more spaced out, and when you have smaller numbers closer to 0, the numbers are closer together. Okay. But we'll take a look. All right, we have to talk about representing a few special cases, and then we'll talk about the denormalized case. Okay. Special values. All right. So if you have 0, and then if the exponent is all full of 1s, so the exponent is all 1s, and the mantissa is all 0s, this is positive infinity. Okay? So in R, if you get too big of a number, it becomes infinity. Right? And then, not -1, but if you have 1 and then all 1s and then 0s, so this would become negative infinity. So again, if the exponent is all 1s and the mantissa is all 0s, then you have negative infinity. All right, and then if you have all 1s in the exponent, and you have something other than all 0s, all 1s and not all 0s, okay, this becomes not a number. Okay, so not a number is type double. It's basically a floating point number. Okay, not a number is a floating point number to represent things that kind of represent not quantities that can't be defined. So, for example, 0 divided by 0 will return not a number. I believe this is from the IEEE 754 1984 specification, and they did it in 1998, I believe, and I think this part changed slightly. It's not that big of a deal, all right? But basically, we represent infinity and negative infinity and not a number using 64 bits, okay? Or however many bits you have in floating point representation. So there's a floating point representation for numbers like infinity, negative infinity, and then the quantity, not a number. And that's why if you ask type of NaN, it's going to say double. And if you say type of infinity, it's going to say double, okay? Because it's not, these aren't like special constructs to R and their data types. These are just values in the double floating points. Okay, which means what is the largest number that is not infinity? Okay, so let's look at the largest positive number that is not infinity. Okay, so that's going to be, okay, for positive it's going to be 0 and the sign bit. And then what's the biggest exponent I can put here? 110, right? Because if I put in 111, it's either going to be infinity or not a number. So here we'll go 110. And then to make it the biggest, we just put in ones in all of these places. Okay, so here I'm going to have a positive, and then this is 4 plus 2 plus 0, so I've got 6, and with a bias of 3, this is going to be 2 to the 3. Okay, and then this part becomes 1.1111. Okay, so I've got basically I've got 1.1111 times 2 to the 3, which corresponds to moving the decimal over, or not the decimal, the binary point over 3 spaces, and I would have 1111.1. Okay, this is fine. Or I could do it the other way and figure it out and multiply it by 8 as well. Okay, all right, well, what is this? This is going to be 8 plus 4 plus 2 plus 1 plus 1/2. And what is that? This is equal to 15.5. Okay, or conversely, I could go 1.1111 times 2 to the 3, and this would be 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 times 8, and I promise you will also get 15.5 if you did that calculation. All right, so this is the biggest number that we can represent in mini float, and if you give it a number any bigger than this, it's going to say that is infinity. Okay, so you're counting, you get to 15.5. What's the next number after that? Infinity. Okay, and it seems silly, and it is. So we would never have a computer system with floating point with only 8 bits. Okay, because it seems ridiculous that the biggest number you can represent is 15.5. But you know, because it feels like, oh, 15.5, that's like way smaller than infinity, right? And it is, okay? But if you think about like, okay, what's the biggest number we can represent on our computer before it gets to, before it becomes infinity? Oh, by the way, this thing is called machine, oh shoot, double max? All right, and so so in the let's see, let's start up R. Oops. All right. So I'll type in dot machine. Oh, is that not? No. Okay, it's dot capital N machine. All right. So if you type in dot capital M machine into R, and so this depends on your chip. The this is implemented double like floating point numbers are not implemented in R, but it's implemented at a hardware level. So your processor inside your computer is what's going to determine how numbers are handled, okay? And so because everybody's computer these days uses a Intel chip, well, I guess there's AMD chips, okay, but pretty much like all of your Macs are Intel chips and almost all PCs are Intel chips. It's going to be the same, okay? You type in capital M machine and it will say all of this stuff, okay? So we have dot machine double X max. This is the largest number we can possibly represent in floating point. And that's basically 1.8 times 10 to the 308, right? And that feels like a big number, but it's also way, way, way smaller than infinity, right? So, you know, with the mini float, the biggest number we can represent would be 15.5. With 64 bits, the biggest number we can represent is around 1.8 times 10 to the 308 power, okay? It also tells you kind of all of these other things, and we'll talk about the X-min and anyway, stuff like that. Okay, so that's I think dot machine, and then you can look it up. So that would be the biggest number we can represent, all right? And now I have to talk about denormalized numbers, okay? So if we put in, well, okay, what would, here, let's just talk about denormalized numbers. Okay. Basically, denormalized numbers, this happens when the exponent is all zeros. Okay, if the exponent is all zeros, the rules change, okay? And what changes is that we no longer assume that the mantissa has a 1 in front of it. Okay, so you've got your exponents and stuff. And what the reason for this is because if we do not allow for this denormalized situation, we have no way to represent the number 0. Okay, because under the regular rules, we always assume the mantissa is led by a 1, right? We always assume that there's a 1 in front of the mantissa. And if there's always going to be a 1 there, there's no way to represent 0. Because you can have like 2 times 1 times 2 to the negative whatever, 3 or something, but that's not 0. Okay, so there's no way to represent 0 if we're always assuming that the mantissa has a 1 in front of it. Okay, so it does make sense to always assume that the mantissa has a 1, but we need to build in an exception so that we can represent smaller numbers and represent 0. Okay, so when the exponent is all zeros, the rules change. Okay, and this is how we are going to do it. So let's just keep in mind what is the smallest normalized number that we can represent. Okay, so smallest normalized number is going to be 0. Whoops. Okay, smallest positive normalized number is going to be 0, 0, 0, 1. Okay, so it's not all zeros in the exponent, and then we're going to have all zeros in the mantissa. Okay, so this corresponds to 1, and with the bias, it becomes 2 to the negative 2. And over here, we're going to have basically 1.0000. And so I have 1 times 2 to the negative 2. And it's positive, okay? So currently the smallest normalized number that I can represent is going to be 1/4. And then we want to get, be able to represent values that are smaller than this, okay? And so when I bring it down to 0, 0, 0, okay, what we are going to do, here, so let me just kind of do this. I got 0, 0, 0, 1, 0, 0, 0, 0. This corresponds to 1/4, or 1.000 times 2 to the negative 2. Okay. And then, let's say we're counting down, okay? So what's the next value if we are counting down, okay? Then what we would do is, if we are counting down binary, we would decrease the exponent, and then this would all become 1s, right? So it's kind of like if you have the odometer running backwards or something, and you had like 0, 0, 0, 0, and you're counting down, it would roll back to like all 9s and things like that, okay? So what we are going to do is, for denormalized numbers, is basically we're going to change the 1 to a 0, and this becomes 1, 1, 1, 1. And we are going to keep it at 2 to the negative 2. Okay, we're going to keep the exponent at 2 to the negative 2, and this would be, this would kind of represent the next smaller number that we can do. Because if I decreased this from 1 to 0, and then I went from 2 to the negative 3, then we're taking kind of a big jump. Does that kind of make sense? So, because everywhere else, if we decrease the exponent and stuff, we're always leaving this 1 in the front, okay? What happens is I'm decreasing the leading digit from 1 to 0, and so this remains at 2 to the negative 2, okay? So the rule is, for denormalized numbers, you have all zeros in the exponent, okay? But now, basically, the exponent is going to be equal to 0 minus 1 less than the bias. So normally our bias is 3. We would subtract 3. But now we would do 0 minus 3 minus 1. So we have 0 minus 2. So we have the exponent is going to be negative 2. So instead of decreasing by the bias of negative 3 as we normally do, when it's denormalized, we decrease by only 2. And this allows us to kind of keep a continuum of numbers without messing things up, okay? And so the largest denormalized number, which is exactly this, 0.1111 times 2 to the negative 2, okay? So this is going to be 1/2 plus 1/4 plus 1/8 plus 1/16 times 2 to the negative 2, and this is 15/16 times 2 to the negative 2, so this becomes 15/64. So basically it's 1/64 less than 1/4, right? So 1/4 is 16/64, and at the next value smaller, is going to be 15/64. And I don't know what that is in decimal, but something, right? I don't know. I don't know what 1/64 is off the top of my head. Okay. So this is the largest denormalized value is going to be 15/64. Okay. And then the smallest denormalized value, and this is going to be the smallest value that we can possibly represent. Smallest denormalized value that is not 0 would be 0, 0, 0, 0, 0, 0, 0, 1. Okay, so this becomes 2 to the negative 2. Okay, and this is going to be 0.0001, and so this is half, quarters, eighths, sixteenths. So I have 1/16 times 2 to the negative 2, which gives me 1/64. Okay, so this is the smallest. So according to mini float, this is the smallest denormalized number. Okay, and then 0 would just be 0, 0, 0, 0, 0, 0, 0, 0, and this would be 2 to the negative 2 times 0.0000. Okay, and that just becomes 0. This smallest denormalized number, this is known as kind of machine epsilon, or I'm sorry, no, machine x-min. This is the smallest value we can represent. All right, and that on our computer is 2.2 times 10 to the negative 308. Okay. Is that all right? There is a concept of machine epsilon, and it's how much, what's the smallest we can distinguish values that are normalized, okay? But here, let me just show you what counting looks like bitwise for our mini float, okay? So we will start, okay? So we'll start at 0. We're at 0, 0, 0, 0, 0, 0, 0, 0, all right? So this is going to be 0, all right? And then we have the smallest denormalized. This is going to be 0, 0, 0, 0, 0, 0, 0, 1, okay? And this we said is equal to 1/64. So it's going to be 0.0001 times 2 to the negative 2. And then the next value, bitwise, next value we can represent would be 0, 0, 0, 0, 0, 0, 1, 0, okay? And this would be 2/64. 0.0010 times 2 to the negative 2, okay? And then the next after that would be 3/64, okay? Basically 0, 0, 1, 1, etc., 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 okay. And then we would count all the way until we get to the largest denormalized, which is 0, 0, 0, 0, 0, 0, I'm sorry, not 0, 0, 0, 1, 1, 1, 1. Okay, and this is 15/64, 0.1111 times 2 to the negative 2. Okay, that's the largest denormalized. And then we have we're at the smallest normalized value. So here we are now at 001, 0000, and this corresponds to 1/4 or 16/64. This is 1.0000 times 2 to the negative 2. Okay, and then the next value would be 0, 0, 0, 1, 0, 0, 0, 1, okay? And if we do this, this is going to be 17/64, okay? 1.0001 times 2 to the negative 2. So far, we've just been incrementing by 64ths. We're going 1/64, 2/64, 3/64, up to 15/64. And then we become normalized numbers, and we're still counting 16/64, 17/64, 18/64, so on and so forth, okay? But let me continue counting, and this is where the floating point system changes, okay? So each increment here, so we are incrementing increment by 1/64, okay? All right, let me keep going. So we have, you don't have to write this one again. So this is 17/64. All right, and then let's keep going, and we're at, so the largest value we can represent here, where we have a 1 in the exponent, so this is kind of largest value with basically 2 to the negative 2. This is going to be 1.1111 times 2 to the negative 2, and that becomes 17/64. Wait, no. 31/64. Okay, so this is right. So this is 1 plus. This is basically 1 and 15/16 times 2 to the negative 2. So it becomes 16 plus 15/16, right? So this is 31/64. Okay, and then the next value here will become 0, 1, 0, 0, 0, 0, 0. Okay, and so this becomes 1.0000 times 2 to the negative 1. So I've incremented my exponent, so now I'm at 1 times 2 to the negative 1, so this is 1/2, or if we're counting by 64ths, this is 32/64. All right, so far so good? Okay, notice next though is my next value will be 0, 1, 0, and then I just increment the last bit, okay? And so this is going to be 1.0001 times 2 to the negative 1, okay? So this is 1 plus 1/16 times basically 2 to the negative 1. And that's going to be 17 30-seconds. Okay? Or at this point, it's 34/64. Okay? So the next value we have increments by 30 seconds. Okay? We're at 17/32. So up until this point, we had been incrementing by 64ths, 1/64. Okay? Now that we are here, and if I count to the next value, 0, 1, 0, 0, 0, 1, 0, this is going to become 18/32. We are now incrementing by 30 seconds. So as the numbers, as we climb the number line, we increment not by the same unit. The number line gets spaced out, okay? And when we get to kind of our largest values, okay, so then kind of our quote-unquote largest values, we said our largest value was going to be 1101111, and we said this was 1.1111 times 2 to the third, which is 1 and 15/16 times 8. And we said this is 15.5, right? Okay. If we think about the next largest value, it'll be 0.1101110, okay? And so this becomes 1.1110 times 2 to the third. And so this is 1 and 14/16 times 8. And this is going to be 15, okay? So when we're at our upper end of values, we aren't incrementing by 64ths or 30 seconds. We are incrementing by halves, okay? And so the number line, the way it looks is it starts at 0, okay, at least for the positive side, and it's symmetric for the negative side, is that in the beginning, our values are very close together. These are, these increment by 1/64, okay? And then we get to a certain point, and then they start spacing out by 30 seconds. Okay, so there's technically, there's going to be, it gets up to, until we're at about 1/2, okay, and then we get up to, I think this is going to be 1, okay, we're spaced out by 30 seconds, okay, and then the spacing gets wider, spacing by 16ths. And then it gets even wider. You're gonna space out by 8ths. Okay, and I think this would take us to about 2, and this would take us to about 4, and so on and so forth. Okay, and basically as the numbers get bigger and bigger, the spacing gets wider. And at any given time, the smallest distance that you can distinguish between two values, okay, wherever you are, is going to be whatever your exponent is, okay? So here my exponent is 2 to the third. It's going to be that times 1/16, okay? So so we have basically our increments at any location, location is basically the exponent value, so 2 to the exponent, cancel, 2 to the exponent times, okay, and in this case, because I have 4 bits, is 2 to the -4. This is number of bits in the mantissa, right? So for large values, we had 2 to the 3 times 2 to the -4. This ended up being 1/2, right? And then for values where the exponent is 2 to the -2, then it's 2 to the -4, and we have 2 to the -6, which is equal to 1/64. Okay, so these are kind of our small values, and you know the next increment. So it's whatever 2 to the exponent times 2 to the number of bits in your mantissa. Okay, And basically, what this is, this 2 to the number of bits in your mantissa, this is kind of going to be known as your machine epsilon, okay? This represents how the values that your machine can distinguish from one another, right? Because when we are at values like 15.5 and we're pushing kind of the upper limit of our thing, we cannot distinguish between values of 15 and 15.5. The machine, if we put in 15.1 and 15.2, in the eyes of the machine, they are the same value of 15, okay? And so you lose anything that requires more precision than what your machine epsilon is. And you can get an idea of the machine epsilon in your computer. Hang on. And that's basically around a little 16 decimal places, okay? So on our computers, we can distinguish values with about 16 decimal places. If we need anything more than that, we can't do it, okay? So if you have a really big number, like 10 to the 300, you can only distinguish the first 16 digits, okay? Beyond that, they're all the same in the eyes of the computer. Okay, we'll end there.